Okay, hello everybody. Welcome to workshop number 5. Today we're going to do a review of the mechanics and the motion that you've learned so far in your physics class. We're going to start out with a couple of different problems. We're going to try to categorize some of these problems and review some of the strategies for you guys tackling these and solving these. So as usual, the best way for you to use this workshop is to pause the recording before we tackle a problem and try to do it yourself. And then only use me for whenever you get stuck or to check that you're doing it in a good way. All right, let's start with problem 1. A building is under construction and a construction worker is standing on top of a 130-meter high elevator shaft. The worker accidentally drops his hammer down the shaft. A, at what speed does the hammer hit the ground? Okay, so give it a pause, give it a go. Let me try it. Like I said, the kinematic equations are going to be key here. What we're doing right here is kinematic 1D problems involving free fall acceleration. So this is motion along a straight line and one-dimensional motion, and we're doing free fall problems. So let's look at these equations. The key with these is always to pick the one that's going to be the easiest for us to try to get us the answer. So they say, at what speed does the hammer hit the ground? So we're going to look for some kind of equation that can pretty straightforwardly tell us the speed based on the little bit that we know. So before we do that, why don't we write down the bit of information that we do know, and then we can try to ascertain what's going to be the most efficient way to find the answer. So a building is under construction, okay? A construction worker is standing on top of a 130-meter high elevator shaft. So there's some height, right? And we drop the hammer from the top of that height. So we could say that Y initial is equal to 130 meters, or we could say that the height of the building, H, is equal to 130 meters. Since it's like the equation here, I'm going to write delta Y. I'm going to write in delta Y. It's going to mirror these kind of kinematic equations that we've already written here. Because I know the hammer is going to fall all the way to the ground. And I know that in order to fall all the way to the ground, it's going to travel from the top to the bottom. That's 130 meters. So I'm going to say delta Y is going to be equal to 130 meters. All right, that's what we know so far. And do they give us any other information as we look through the problem? The worker accidentally drops the hammer down the shaft. That's all they tell us. So we're going to drop the hammer. So there's some other information here. There actually is. Yeah. Let's say. So we drop the hammer, right? We don't throw it down the shaft. So initially, can't we say that the initial velocity is equal to just 0? Don't we just drop it? Doesn't it just start with no velocity? And then the only thing that's making it fall is gravity, right? We didn't force it to go down. Only gravity did that. So initially, the velocity is 0 meters per second. Note that there. Okay. Any other information? Well, we maybe know a couple of other things. But we know usually the strength of gravity. We know little g, the acceleration due to gravity. Maybe we'll use that. Let's write this down just for now, and let's see what we can pick out. So if we look at the first equation, this one tells me the final speed based on the initial speed, based on the acceleration, and the time. So that seems pretty good. So I want to find VF, right? At what speed does the hammer hit the ground? That's what I want to find. So this would tell me that. In order to find it out, I would need to know the initial velocity. I do know that. That's good. And I would need to know the acceleration. I do know that. That's a little g, right? We're going in a negative direction, so minus g. But do I know the time? I don't know how long it's going to take for the hammer to hit the ground. So maybe let's not use this one. And you know, sometimes you can solve these problems by picking an equation that's not the fastest or the easiest, and you can work it out, and we could maybe solve for t a different way, and we could get to the answer eventually, and that would be fine, and that would be totally fine. But you can save yourself some time and sometimes a lot of headache by going and looking through these equations and seeing which one is going to be the most direct from the start. So this one says delta x, but we know in our problem it's delta y, right? We're not traveling in the x direction, we're traveling in the y direction. In either case, it's a one-dimensional motion. It's exactly the same. So we replace this with delta y. We do know delta y. And just say delta y is equal to the final speed, v, plus the initial speed divided by 2 times the time. So I like this one. I like this one. It's got all the pieces that we need, but again, it's got the time in it. It's got the time in it, and this one has the time in it. Is there anything that doesn't have the time where we know everything else? Where we know everything else? How about this one, number 4? Number 4 says, what is the final velocity squared? Well, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration times the distance traveled. So this one, I think we know everything. We know the initial velocity, and it's 0, so that's even easier. That's just going to go away. I'll erase that in case we want to look at those later. It's going to go away. And then we know what A is. We know that A is just going to be G. It's going to be G. And we know what delta Y is. We know what delta Y is. So I think we can straightforwardly solve from here. So let's try this. Let's say V squared, okay, is going to be equal to 0. 0 squared is going to be 0. So I'm just going to leave it off. I'm going to leave it off. And then I'm going to say 2G times delta X, which is times 130. So really, this was just 260 times G, right? And that's the square. So we want not the square of V. They didn't ask us what is V squared. They asked us what is V. So we can say V is plus or minus the square root of this quantity, 2G times 130, or 260 G. Okay. Now I'll encourage you to punch that into your calculator. I'll do the same. Let's see what answer I get. The square root 260 times 9.8, let's say. Okay, and I'm coming out with a velocity of 50.47 meters per second. And is this plus or minus? Well, it's going down, right? It's going in a negative y direction. So we should say negative 50.47 is the velocity. And what is the question we're trying to answer? We're trying to answer about the speed. And what is the speed? It's just a velocity without regard to direction, right? The scalar version of the velocity. The magnitude of the velocity. So the velocity is negative 50.47. We could round that up. Let's see, how many sig figs did they give us? They gave us, well, we used 9.8 for gravity, so we're using 2 sig figs. Let's just say 50.5. The velocity is negative 50.5 meters per second. So the speed is just 50.5 meters per second. Okay, let's do the next one. How much time passes between when the hammer is dropped and when it hits the ground? Okay, so now they are asking us for the time. If we would have done this the long way around that I mentioned, we would have answered part B first. So now we're looking for a different equation. We're looking for one that has the time in it. We're looking for one that has the time in it. How much time passes between when the hammer is dropped and when it hits the ground? So we need to travel that full delta y. We know our speed. We know quite a bit. What equation do you want to use? Looks like we got some options. We know the final speed. We know the initial speed. We know the acceleration. We know the time. This one looks pretty straightforward to me. We could use that. We know this one, and number 2. We know everything in there except for t. We could use number 2 as well. Number three we could use, but this is quadratic, so it's a little unnecessarily difficult, but we could do it if we wanted to. We know everything in there. And then number 4 doesn't have any mention about the time, right? It's kind of irrespective of the time, so that doesn't help us. Let's use number 1. Seems pretty straightforward. So we just found that VF was equal to 50.5, right? So from the kinematic equation, we have that VF is equal to V initial. That was just 0, right? That was just 0. So VF is just equal to AT, which is really just GT. There we are. So if we divide the velocity by G, we divide both sides by G, we lose G on the right-hand side. And we just have VF divided by G is equal to T. We'll punch that into our calculator real quick. We're just going to divide our previous answer by little g. And I get 5.15 seconds. 5.15 seconds. That's a pretty substantial time to fall. Things tend to fall pretty quick, but we were 130 meters high, which is quite a ways. That seems pretty reasonable to me. That seems pretty reasonable to me. Let's check the next one. Let me give myself some space here. Do an insert. Okay. So it says, what fraction of the total airborne time does the hammer spend in the top 75% of the falling distance? Okay. Oh, I love this one. I work with students on this type of question quite a lot, and I think the percentage was confusing. I remember finding this type of question confusing when I was initially doing some of my courses. So, but it turns out it's not so difficult. So let's try to handle it. First, give it a go. Give it a go. See if you can think of how we're going to answer this question. Okay, now let's work through it together if you've given it a try. So what fraction of the total airborne time does the hammer spin in the top 75% of the falling distance? So the final answer that they're looking for is they want a fraction. They want the time in the top 75. So let's call it t.75, the time to fall the first 0.75 of the distance, divided by the time total, right? The total time to hit the ground. Maybe we give that to them as a percentage. Maybe we leave it for them as a fraction. But this is what they're asking. This is what they're asking us to find. We already found T total. We already know what this is. So all that we need to find, the only question mark here is, what is T.75? What is T.75? Okay. Now, how do we answer this? The top 75%. Let's do a little intuition check, right? First of all, should the answer to T.75, should it be less than the total time, or should it be more than the total time? Well, it's got to be less, right? It needs to fall just a portion of the distance, not the full distance. And that has to take less time than it took to fall the full distance. It's the only way this is going to make sense. We should end up with some kind of answer like that. And really, we can just do the exact same thing that we did previously. But now, instead, we're just looking at how long it takes to fall 75% of the distance. So what is 75% of the distance? Well, delta y was equal to 130 meters. 130 meters. So 0.75 times delta y is equal to what? Let me do a little multiplication. Okay. Sorry for my ugly handwriting, guys. I usually work on paper. 0.75 times 130 meters is going to be 97.5 meters. So now we're just asking, how long does it take to fall 97.5 meters? Okay, how do we want to answer it? Let's look back at the questions. So we're going to use a different change in x, right? And now if we wanted to use this final velocity, we couldn't use the final velocity that we found when we were hitting the very bottom, right? That would be different from the velocity that we reach when we're 75% of the way down. It would be lower, right? It wouldn't have fully accelerated. It wouldn't have accelerated for as long. So maybe I'm liking one of these that doesn't have that. Okay. So we're looking for the time. But we're going to have to go ahead and find the new final velocity anyway. So we'll do this in two steps. It's basically just like doing part A and part B over again with different numbers. So let's do it the exact same way that we did it before. We'll get a little extra practice. So when we were finding how long does it take the hammer to hit the ground, now we're answering the question, how long does it take the hammer to fall 75% of the way? Let's do part A At what speed does the hammer reach? What speed does the hammer reach when it's 75% of the way to the bottom? That's the question one. We're going to use this same equation. We said that it was V is equal to plus or minus the square root of 2G. Now this time, not times 130 meters, but times the traveling a distance of 97.5 meters. Let's punch that into the calculator. We take the square root. We do 2 times 9.8 multiply by 97.5. I punch that out and I get 43.7 meters per second. A lower velocity like we expected, 43.7 meters per second and change. Okay. And then what did we do? What did we do in order to find the time, this travel time? Well, we divided the velocity by g. And if you don't remember how we got there, just work back to it. It's real quick. Work back to it. It's real quick. We're just going to divide this velocity by g. I'm just going to punch that straight into the calculator, and it's going to give me the time. We do the answer, 9.8. And the fall time is 4.46 seconds. 4.46 seconds. Okay, now before we look at this fraction, let's think about one more thing, one more intuition check, one more gut check. So how do you think that this fraction is going to relate? Do you think, let's compare it to 75%. Do you think it will take 75% of the falling time to cover 75% of the falling distance? Or will it be less than 75% of the falling time to cover 75% of the distance? Or will it take more than 75% of the falling time to cover 75% of the distance? Think about that. So as the object is falling, it's accelerating. It continues to go faster and faster. Initially, it's kind of slow. And by the end, it's going the fastest that it's been going the entire time. So what we should find is it takes more than 75% of the time for it to follow the initial 75% of the distance. Because that last 25% is when it's going the fastest. So it has very little airtime to cover that final little bit of distance, at least. So let's see exactly what this bears out. If we divide 4.46 by 5.15, what does that give me in my calculator? We have the answer. I divide it by 5.15. I get about 0.86, which is exactly matching our prediction. I get 0.86. which is to say, multiply by 100, that is to say, it takes 86% of the falling time. Actually, I think if I round this, 86.6, we could say 87%, let's round. Just get a nice 2-digit finish here. I'm just rounding up. It takes about 87% of the falling time to cover the first 75% of the distance. Cool, I love that one. Let's go on to our next one. Problem number 2. What are we going to look at? Let's see. It says kinematics, 1D problems involving instantaneous velocity and speed. Let me bring it to you. Okay. Okay, let's get that of a size we can read. All right. So this is more one-dimensional motion problems, more one-dimensional motion. This one is involving instantaneous velocity and speed, different concepts. Categorize our problems and make it easier to solve them. Okay. The position of a particle is given by x is equal to 4 minus 10t plus 2t squared minus 3t cubed, where t is in seconds and x is in meters. So really this is x as a function of t. As t changes, x changes. And then the question they ask us is, what is the velocity of the particle at t equals 2 seconds? Okay, all right. So what are we going to do here? We use the kinematic equations when acceleration is constant. The information that they've given us here, I don't think that indicates a constant acceleration. I haven't taken the derivative yet, but I see a cube over here, so I'm suspicious that we would get a constant acceleration. Now, what does this mean? This is some function where someone has viewed the path of a particle, the position of a particle specifically, and they noted the position of the particle in space at each instant in time. And then they mapped it out and they said that it follows this function. It obeys this function. So if I tell you what time, you can predict the position of the particle. Now they ask us, what does that tell us about the velocity? What does that tell us about the velocity? And for this, we're going to need calculus. We're going to need calculus because we can see there's changing rates here, right? The position of the particle is changing with respect to time, and it's changing in different ways. It's changing in different ways. So when they ask us, what is the velocity of the particle at t equals 2 seconds, they're asking us, what is the instantaneous velocity? What is the velocity at that exact instant when the time is equal to 2 seconds? When the time is equal to 2 seconds. Maybe this brings to mind some images of, you had these X versus T graphs, you had V versus T graphs, you had all kinds of graphs, right? And you drew these graphs, and maybe the position was something like this. And then you said, what's the velocity? And it was connected to your ideas of calculus. And what you learned, one of the things that you learned was that if you took at any point in time, and you took some tiny instant in time, some little tiny dt, right? And you looked also at some little tiny change in x, some little tiny dx, then the slope presented by that little change would be the tangent line. And then the tangent line would be equal to the velocity at that instant in time. Or specifically, that there's this relationship between, if we have x as a function of t, x being position as a function of time, then we have that the derivative of the position as a function of time, x prime, is equal to the velocity as a function of time. Or I could say dx dt is equal to v of t. So if we want to find out information about v, we need the derivative of this function instead of this function itself. So let's take the derivative. The derivative of this function, well, we take 4 is a constant, it becomes 0, minus 10t. We drop down an imaginary 1, we do 10 times 1, it's still negative 10. And then t times 0 is 1, this becomes negative 10, the t disappears. All right, just doing the power rule here a couple times. We do 2 times 4 is 4 times t. If it looks like any kind of magic, what I'm doing, then just review your calculus. Okay, 9. Specifically, look at the power rule. Look at the power rule. I'm just following the power rule to quickly obtain the derivative. This is 3 times 3 times 3. T to the 3 minus 1 is t squared. Okay, did I do that right? Yes, I think so. And they say when t is equal to 2. So I already said how the derivative is equal to v of t, right? V of t. And what do they ask? They ask, what is v of 2? What is v of 2? So we just go equals 0, this is minus 10. We plug in a 2 here, so this becomes plus 4 times 2 minus 9. Oh, I almost said 4 because my number looks so bad. Okay. 4 squared. 4 squared. What's that going to equal? We'll punch it into our calculator. I could do the arithmetic also, but I won't. We're going to do minus 10 plus 4 times 2 is 8 plus 4 times 2, and then minus This is 9 times 4 squared, which is going to be 16. 4 squared is 16. Oh, you know what? I plugged in a 4 here. I was supposed to plug in a 2. I was thinking 16 sounded too high. This is because I squared it in advance in my head. So this is 2 squared is actually 4. So we have 9 times 4, not 9 times 16. Pardon me. You probably saw that already. Okay, so I punch that and I get negative 38 meters per second. Negative 38 meters per second. And then they ask us, is the position of the particle increasing or decreasing? Is the position of the particle increasing or decreasing? Well, the velocity is negative. The velocity is negative. So that means the velocity is trying to make us go in the negative x direction, right? It's taking us this way. So if we're going in a negative, if we have a negative velocity, then the particle is traveling backwards, it's traveling in the negative direction. So it's not increasing, it's decreasing. It's decreasing. At least at this particular point in time that we analyze. What is the speed of the particle? That's equals to. This is just a question of vectors versus scalars. So we said what the velocity was. We said the velocity was negative 38. Then the speed of the particle is just the scalar version of that. It's the magnitude of the velocity, irrespective of distance. It doesn't say in a negative direction. It just says it's 38 meters per second. 38 meters per second. And we're done with that one. Pretty easy. Pretty easy. These one-dimensional motion ones are not so bad. You just have to be solid on what it means to be a vector, what it means to be a scalar quantity, and also be solid on the kinematic equations. Be ready to employ them, be ready to use them. Let's take a look at something a bit more involved, maybe. We're going to go into 2-dimensional and possibly 3-dimensional kinematics, kind of the next level up. We were looking at just one direction. We were only allowing things to move in a line. Now we're going to allow them to move in multiple dimensions at once. And we're going to consider how that works. Okay. 2D and 3D problems. A plane flies, okay. A plane flies 300 miles east. Okay, let me get out some arrows. It's going to be arrows for you guys. Okay. A plane flies 350 miles to the east. Oh, that's not an arrow. Draw. Insert an arrow. 350 miles to the east. This is going to be my 350. Okay. And then can we get another arrow in here? It does that in 50 minutes. It does that in 50 minutes. And then we have a second vector because we travel 500 miles south from airport B to airport C. And that takes us 1.8 hours. 1.8 hours. All right. 1.8 hours. Okay, so let's think about these rates. Actually, I assume we're going to think about these rates. Determine the displacement vector. Oh, okay. Well, we're not going to think about any rates yet. Determine the displacement vector. That means come up with a vector that tells me how much the position of the plane has changed after the whole flight. So but we started over here, right? And they say, give me the vector that takes me to point C, airport C. We traveled from A to B and from B to C. So give me the vector that goes straight along that line. Maybe I'll do this one in green. Okay. We're looking for this displacement. This displacement. Okay. There we go. All right. So this is pretty straightforward. Let me maybe type it out let me maybe type it out. Okay, there we go. All right, so we travel in 2 different directions. We want a vector. They want a vector for the displacement. So the displacement vector, let me just do a bold S. It's going to represent that. It's bold because it's a vector. S is for the displacement. I'm going to put this in brackets. We can see it's also a vector. And the answer is just that we travel 350 miles to the east. So let's pick a coordinate system. Let's pick a coordinate system. I'm just going to say this is the y direction. This is the x direction. This is x. This is y. Pretty standard fare right there. Okay. I'm going to do draw. Okay. I'm going to go back here. Back to work on that. Okay. Okay. So we got our vector here. We travel 350 miles east. That's in the positive x direction. So 350. And this is in the direction of, I'm going to call x hat. X hat. Can I do an x hat here? Insert equations. Equation. Okay. I'm not seeing any vector script here. I'm not seeing. It'd be better if I draw it. I'll just write it out. 350 miles. X hat. Or maybe you wanted to write I hat. That would be the same thing. That's fine. This is the unit vector in the x direction. The I hat would be the unit vector in the x direction as well. Same thing. Okay, so this is our displacement vector. And then we say comma, and we go 500, or we're traveling in the negative y direction, right? So negative 500 in the y hat direction. And there's our vector. It's as simple as that. This vector tells me exactly how to get to this point C. You travel 350 miles in the x direction, which is east. And then you travel negative 500 miles in the y direction, which is south. Determine the average velocity vector for the total trip. Determine the average velocity vector for the total trip. Okay, I'm going to try to speed up a little bit, guys, because I want to get through a few more questions. Average velocity vector for the total trip. Let's see. Determine the average speed. We may skip a few of these. We'll leave them up for you. We've also got the answers that I'll post at the end, so you can reference any of the ones we don't go over. Average velocity vector. So this is, we can imagine it as the green arrow still. Now we just are concerned about the rates. We have the displacement. Now we want to think about a displacement over time, which is a speed, right? The velocity is going to be the same direction. So really all we have to do is take this same answer. Let me just copy it. Actually, let me leave it for you to do as an exercise. All you're going to do is translate this now into a velocity, which means take into account the time. This is 50 minutes. Maybe you want to translate that into hours. Maybe instead of miles and minutes, we can say miles per hour. So how many hours is 50 minutes? So it's a little less than an hour, some decimal, some fraction of an hour. And then 1.8 hours. We can find those rates. We can find the average velocity vector, which is the same as this displacement. It's similar to this displacement. It's just the velocity instead of the displacement. Okay. Moving on. This one's straightforward. I think you guys got that one. Okay. Alrighty. Okay. Skipping on down. Let's get to the next one. Okay. All right, we're going to do this uniform motion one. And then if we do have time, there's a fun one for us to do at the end. But we definitely want to get in at least one circular motion problem. So kinematic problems involving uniform circular motion. We talked in the last workshop about the analogs between linear or tangential motion and your run-of-the-mill circular motion, uniform circular motion. We'll go over some of that again. We'll do a little bit of a review. The question says, a fan rotates at 1,000 revolutions per minute. All right, 1,000 revolutions per minute. The tip of the blades have a radius of 0.2 meters. What is the distance traveled by the tip of the blade during one full revolution? So this is a question of arc length. We talked about this a little bit last time. The arc length we denote as S, right? It's kind of like a change in position. It's a change in a position over a circle. It's the sweep of an arc. And the arc length is related to the amount of angle that we turn by the radius and the amount of angle. It's proportional to the amount of angle that we turn. And the constant of proportionality is the radius, I could say. So we just multiply r theta in order to get the arc length. So what is the distance traveled by the tip of the blade during one revolution? Well, in order to do a full revolution, we travel 2 pi radians, or 360 degrees. So that's theta. What did they say r was? They said r was 0.2. R was 0.2. If we just simply multiply that out, we'll get the arc length over the full rotation. We just do 0.2 times 2 pi. And that is about 1.25 meters. .25 meters. Okay, what is the speed of the blade tip? What is the speed of the blade tip? You try that one, you tackle that one. Think about what we built on, what I just discussed, and see if you can build it up to velocity. You notice a lot of these motion problems follow a similar path. They ask you first about something about position, and then they maybe ask you about speed, and then they maybe ask you about acceleration. And that's a really logical and easy way to go through a problem, because usually, well, we know that the position, right? The velocity is the derivative of the position, and the acceleration is the derivative of the velocity. They're kind of stacked on top of each other in one way, and you can go back and forth between them. The easiest way to do that is usually to go position, speed, and then acceleration, or velocity, acceleration. So what is the speed of the blade tip? I'll leave this one for you to do. Okay, you've had a try at it. I'll leave you to punch out the calculation, but I'll write for you this equation, which is going to be that V, now V is replacing S, is proportional to omega. Omega is the angular velocity. So if the angular velocity increases, the speed at the tip of the blade increases. And it's proportional, but based on a constant proportionality based on the radius. So as the radius grows, we travel a greater arc length in the same amount of time, the velocity increases as well. So V equals R omega. And you can solve from there. You need to think about what is omega, and you need to think about translating it from 1,000 revolutions per minute into some standard units. You need to eventually get to a meters per second. I'll let you think about that. What is the acceleration of the blade tip? What is the acceleration of the blade tip? This is where I think some students can get confused. It can be a little bit confusing. So it's traveling at 1,000 revolutions per minute. That's just is its speed, right? It's not slowing up, and it's not slowing down, and it's not speeding up. So you might be tempted to say, well, there's no acceleration. There's no acceleration. But that's not true. That's not true. Whenever something has its velocity changing, there is an acceleration. Whenever something has its velocity changing, there's an acceleration. And remember, there's two components to the velocity. There is the direction, and there is also the magnitude, the direction and the magnitude. So we can change our velocity in two ways. We can change the size of the vector, that is the velocity, or we can change its direction. And again, we discussed this in workshop 4, and we're running out of time. So if you want to see this in more detail, think about looking at my recording for workshop 4. We're looking online. There's tons of good explanations for this. But it is something to be cognizant of, because it can be a little tricky. We can change the velocity in two ways. But whenever a velocity is changing, it's always due to a net force. It's always due to a net force, which is resulting in an acceleration. So is the acceleration 0? No, it's not. Because what is the force? What is the acceleration that is responsible for changing the direction of the velocity. And you're going to think about that. You're going to think about that. I'm going to post up the answers. I'm going to go over the last question. We're unfortunately out of time. Sorry, guys. I think I spent a little bit too much time on the initial problems, or maybe I'm always just too ambitious and I put too many problems for us to try to get through, but there's so many good problems to solve. So it's a tempting, difficult problem. It's a difficult situation. Let me scroll down. I'll give you guys this one. It's a fun one. I had fun with this one. It's a little bit of a complex situation. You see this diagram has lots of different numbers all throughout it. We can break it down. It's not so bad. I would just encourage you to be very consistent and thoughtful when you're setting up your X and Y axis, and then be careful when you're applying your signs. And I think you should be able to get the right answer here. This question is, a ball rolls down a ramp that is inclined at 15 degrees with a horizontal. At the edge of the ramp, point A, the velocity of the ball is V naught. Determine the range of values of V naught so that the ball enters the horizontal pipe as shown. So we're looking for some velocity such that the trajectory of the ball continues and it lands in this pipe, right? It doesn't fall down into this pit. It makes it into the pipe. And we could imagine a velocity that's like so high that it shoots in straight in, right? Maybe it shoots in like straight in and it almost clips the top. So the very highest we could go is the very top of this pipe. And the slowest we could go, or the lowest that we could go, is the bottom of this pipe, right? And you kind of intuitively know, if this rolls too slow, it's just going to fall into the pit, right? If it rolls too fast, the drawing is not to scale. It kind of doesn't look like this would be the case. It kind of looks like if it rolls super fast, it'll just go straight in. But the drawing is not to scale. If this rolls too fast, it would just overshoot the pipe. It would just overshoot the pipe. It would just go straight over. So we need to find some range of speeds such that we land in the pipe. We need to find some range of speeds that we land in the pipe. You're looking for a lower limit and you're looking for an upper limit. Consider looking for a height maximum and a height minimum, and then using your kinematics. And this is a 2D motion problem. It's a 2D motion problem. So hopefully you've paused and you're not listening to me giving you all these hints. But if you've already worked on it, then go ahead and listen to me give you some hints. You're going to need to consider the X direction, and you're going to need to consider the Y direction, and you're going to need to consider the component of V naught that is in each of these directions, right? It's pointed at an angle. So some of V naught goes in the downward direction for Y, or maybe you want to call it the upward direction. You define these. I think if I were to set this up like this, let's see, if I were to set up my coordinate system, just for my ease, I might say this is positive Y and this is positive X. Kind of the flip of the convention, but I think it makes the problem a little easier. Do whatever you want, but you have to be careful about noting what these are, noting what the values of the components are. And then you need to match them up. You need to match them up somehow. That we travel this distance in X without falling too far in Y. We travel the whole distance in X without falling too far in Y. So I will leave you with that. The last thing I'll post on this recording is the answer sheet for you guys to check your answers. Okay. And we'll continue to do more of these problems. We'll continue to keep working on what you're working on in your classes. And additionally, eventually, we're going to do some more reviews, which will continue to be comprehensive like this. We'll go over a bunch of stuff. Okay. Here's our answer key. 50 to do. It looks like all the same answers that we found. Huzzah. I think we did good. Here's your answer key. You can check against that. I'll scroll up one final time. Take your screenshots, pause where you need, work what problems you will. The key to all these is practice. The key to all these is practice and just being careful. And they're not too bad. Okay, good luck, guys. That's it for today. Hope to see you in the next one.